So this will be a first in a series of videos talking about representation theory of finite groups. But first, we want to introduce roughly, very roughly, what a representation is, and concentrate more on the motivation of why you'd want to study it. And then later on, we will consider a much more rigorous and much more precise definition of what we mean by representation. But let's begin by roughly stating what a representation is. So what are the ingredients? So we have a group G. So let G be a discrete group. Then a representation will be a mapping from G to linear operators acting on V, which is a vector space. Now, specifically, we get a G in G, and then this tells us that we must produce a TG that will act on V. This representation can be labeled, and I can call it, for example, gamma or something like that. Okay, so a bit more formally, we have representation gamma going to, let me call this linear operators acting on V, G, L, V, and it takes specifically G and produces some element TG. Now, this is not there's more to the definition of representation, but for now we'll simply stick with this. Again, this is very rough. We're trying to motivate what a representation is and roughly state what it is. Okay, so now why would you want to do this? Why would you want to get a group and then for each group element produce a linear operator corresponding to that group element? So let's consider the system. You have a ball here, a mass contained with a spring, and you have this little letters 1 and 2 with a spring constant K. So we can write down a Lagrangian for this, and this will be something like this. Here, T quite obviously should be something like that. And if you think carefully, you'll find that U is something like this, and X is X1 and X2. This is the position for the first mass, position for the second mass, and of course X dot will be X1 dot and X2 dot. So there's a reason I'm writing things this way, which I'll state more in a moment. But let's write the Newton's law version of this. In coordinates, we'll have something like this. Something like that. So This is a series of coupled ODEs. Okay, and of course, to make our life simple, we need to decouple them. So decoupling them, you can see, will mean finding some coordinate system such that this interaction, this potential U, is diagonal. So decoupling will mean diagonalize U, which means find new coordinates, eta 1, eta 2, such that ODE are decoupled. Okay, so why did I write things out this way? We can already see matrices, we can see column vectors, so there is some vector space. This vector space will roughly represent the equation of motions. What I mean to say is that if I have a vector space V, this will be, for example, R2, and then in R2 there'll be vectors which will correspond to the positions of the masses. In other words, what I'm going to have is x1 of t and x2 of t, and this is a vector in R2, and this is a vector space, R2. Now, there is something else that can be said about this system. So we have identified a vector space, but remember, we want to connect this somehow with the language of a group somewhere. So a representation is a mapping from a group to a vector space. We can see the emergence of a vector space here. Our solutions are in this vector space, so where does the group come in? Well, if you think about this system, it turns out that we can analyze this in a slightly different way. Let's consider the system again. We have 1, we have 2, we have the coupling, and let's say we have initial velocities this way, and let's say that way. So V1 and V2. Now let's do a symmetry operation. After all, our system does have a symmetry. So, for example, let's call it OS. So what kind of symmetry does our system have? Well, it turns out that it doesn't matter what we call 1 and what we call 2. We can call this 2, and we can call this 1. But if we call the first one 2 and the second one 1, sorry, mistake. This has to be V1, V2. If we call this first one 2 and second one 1, then it means that we must switch what V2 is and switch what V1 is. These systems, CS1 and S2, are completely equivalent. The equations of motions for S1 and equation of motions for S2 are exactly the same. Nothing changed. So the idea that I can switch, relabel my masses obviously can be encoded in a group. So a physical symmetry operation is encoded in a group. So here a group would be a symmetry group acting on two things, which is S2. It's an abelian group. And somehow this symmetry operation I encoded in this group meant that somehow that the vector space, which has our vectors corresponding to our solutions, did not change. The equations of motions did not change. Now, we know that, so somehow what's happening is that we have a group and we have symmetry operations. These correspond to like physical actions. What did I physically do to my system? And this meant that the vector space, which has vectors which correspond to our solutions, this meant that I could find some linear operator acting on V. More specifically, it's going to act on our small vector V that contains, which has as its components the equations of motions. So this can be a linear operator acting on V that leaves equations of motion invariant. Okay, now you can see already that if we're to find exactly what the symmetry operations correspond to in terms of linear operators, this will be our fabled representation. So this is representation gamma, for example. Okay, I'm calling it gamma. Now, how will this work more specifically? So we know that if I have an operator, let's say A, then it has eigenvalues and eigenvectors. And it's a theorem that I can write, and so this A acts on, A will act on some vector space V. Let me write this a bit more neat. And so there's a theorem that tells me that I can decompose this V as a direct sum of the eigenspaces of this linear operator. So lambda is an eigenvalue, and V lambda is an eigenspace. So if I go back up, I have my group, which encodes my symmetry operations. There is this representation which maps the symmetry operations to some linear operator that acts on a vector space. This linear operators will act on this vector space, and it will have the effect that will leave my equations of motions invariant. Supposing I were to diagonalize this linear operator and get, roughly speaking, its eigenvalues and eigenvectors, then I could, in a way, decompose my equations of motions into parts that, in a way, do not talk to each other. They transform under different kinds of symmetries. So what I mean to say is that we have this group of symmetries. It acts on this vector space, but I can write this vector space as a direct sum of some eigenspaces, and in each eigenspace I can decompose what the system is doing into sort of spaces that don't talk to each other. So what this is reproducing is the idea of the normal modes that were introduced earlier, which I called Eta 1 and Eta 2. So what I'm trying to say is that the idea of diagonalizing my equations of motions is very much connected to the idea of getting some symmetry operations, finding how they act on our vector space, and in some fashion diagonalizing the vector space. When I diagonalize this linear operator, and therefore find a direct subdecomposition of my vector space, this gives me parts of the vector space that don't talk to each other. And this, I claim, is equivalent to finding these new normal coordinates that decouple this ODE. Now, I'm being very vague here because I don't want to introduce many terms that don't make much sense at the moment. But these subspaces that I'm talking about in this V lambda will correspond to vector spaces that are acted on by the irreducible representations that make up this representation. And all this will be made more explicit later on.